Hello, and welcome to Shiksha Costa. Today we're going to be learning about where exponential relations are applied in real life. So today we're learning about exponential relationships as they happen in real life. How do you know you're successful with these skills? Well, throughout this lesson, you're going to be able to collect data that can be modeled as an exponential relation. You're going to do this with through an investigation, and sometimes these investigations could or could not use technology. It's up to you whether you want to do it. And you can collect that data from either a primary source, or you can go right to using secondary sources. The important thing is that once we're done collecting that data, we're going to graph it. Then we're going to describe some characteristics of those relationships by using tables of values and graphs. To start off, to get our minds activated and working in the right ways, in that good way, let's look at this graph here and ask ourselves a question. In this graph, what is happening to y as x becomes larger? Take a minute to think about this. Remember that this is the x-axis. So these are the values of x. These are the values of y. This is the y-axis. So each coordinate here, this coordinate has an x value of 0 and a y value of 100. This one has an x value of 3 and a y value of 60. So just pause the video here and think about for 1 minute what happens to the y values of these coordinates when their x values get larger. I think the most obvious thing, if you noticed, is that they are going down. As x gets larger, the y values seem to be always decreasing. One thing you might notice by looking at this graph is it kind of looks like the graph of an exponential relationship, but it's like reversed, right? It's going down instead of going up. And in fact, as x gets larger, the y values, they are decreasing, and just like but very similar to how the graph of an exponential would work, they don't decrease by the same amount. In fact, the first decrease is quite large. The next one is a little bit smaller. The next one is a little bit smaller and smaller and smaller until it seems like it will not go past this line right here. It seems like it's decreasing in a way that it will not, the y values will not get lower than 20. So we could say that it looks like as x gets larger, the y values will decrease by a smaller and smaller amount each time, getting closer and closer to the value 20. So let's move to an investigation here. And in this experiment, which you could do at home if you like, a thermometer was placed in a hot cup of coffee and the temperature was recorded over time. So every 3 minutes you can record the temperature. And again, this is an experiment that you can do at home if you have a thermometer and a hot cup of water or coffee or anything like that. At the start, the temperature of the cup of coffee was 100 degrees Celsius. And you can record this every 3 minutes, and hopefully it should take you exactly 27 minutes to complete this experiment. And if you did complete this experiment, you might see something like this. After 3 minutes, the temperature of the cup of coffee was 61 degrees. After 6 minutes, it was 41 degrees. So you can see the thermometer is dropping. After 9 minutes, it dropped a little more to 31 degrees. After 12 minutes, 25 degrees. 3 minutes after that, it was 23 degrees. 3 minutes after that, it was 21 degrees. 3 minutes after that, it was still 21 degrees. 3 minutes after that, after 24 minutes, it dropped to 20 degrees. And finally, at the end of the experiment, after 27 minutes, the temperature in this cup of coffee was still 20 degrees. What do you notice about this table of values? So what do you notice happen here when we observe this table of values? One thing you might notice is, of course, that the temperature drops very quickly at the start, and then towards the end, in the last 15 minutes, it drops quite slowly. And in fact, if we were to take all of this and put it on a scatter plot, we would get something like this, wouldn't we? Right? And this was exactly the graph that we just examined in our mind's eye. I wonder if we kept tracking the temperature according to time, would this eventually just keep staying the same at around 20, or would it drop below 20, and why? I think if you think about this a little bit deeply about the fact that this is a real thing that's happening, and you would notice this in an experiment, is that this cup of coffee would not go below 20 degrees because that may be the temperature of the room. Right? In this experiment, it was the temperature of the room. The other thing to notice here is that this relation actually is exponential. Whenever an exponential relationship is decreasing like this instead of increasing, this is called exponential decay. Exponential relationships, they happen all the time in real life when things increase or decrease by a percentage or by a factor. In other words, by multiplying repeatedly. Exponential decay is what we looked at today. That's when a value is decreasing exponentially. And an example of this might be an item that is cooling to room temperature, right? The temperature change slows down the closer it gets to the ambient temperature. It could also include, another example would be the intensity of light as it passes through glass or water. Remember, the deeper underwater you are, the darker it is. There are some fish that live at the bottom of the ocean and they actually create their own light. It's called bioluminescence. Because down there, the sun's light has to go through so much water that it is not intense at all. It's very dark down there. Another example might be the mass of a radioactive isotope. So usually when archaeologists are, they're opening up tombs and they're opening up caves and they're trying to find, oh wow, we found some ancient Neanderthal skeletons in here, some tools. I wonder how old this is. What they will do is they'll take a sample of something like carbon. Carbon decays, and they can use how much carbon is left to figure out exactly how old that skeleton is. Isn't that crazy? The dependent variable, so in our example here, we said time and temperature is what we were tracking. The temperature of the cup of coffee depends on the amount of time that has passed, right? The dependent variable will always approach, but it will never actually reach that lower limit. Okay? So this cup of coffee would have never gone below 20 degrees Celsius because it's warmer than 20 degrees and the room is just 20 degrees. There's nothing to pull it past 20 degrees Celsius below that line. The other way around is, of course, exponential growth. Exponential growth happens when a value increases exponentially, and that includes stuff like investments, debt, bacterial growth. Bacteria grows very fast. Every so often they double, or even the growth of cancers. Population growth. So like the city of Toronto might grow by 0.5% every year. And that number will be growing. It'll grow just like this curve, except backwards. It'll grow exponentially. The equations of exponential growth or decay are given, we looked at these earlier in the unit, a times b to the power of x, where this number b here, this is 1 plus or minus r. Now hang on, what is r? R would be the growth or decay rate as a percentage. So we always express the growth or decay rate as a percentage. If it's a decay rate, in other words, if it's going down, then that's why we would use minus R. If it's a growth rate, we would use plus R. Let's look at an example of this. In this example, the value of one share of Lariat Studios, remember this is, earlier in this unit we talked about investments, right? So this is one little piece of this company. It grows according to this equation. And as we've studied in exponential graphs as well, we can already tell quite a few things just by looking at this equation. X is the number of years since 2010. What is the growth rate per year? Before we get to that, I'm going to ask another question, see if you can figure this out. How much was Lariat Studios worth in 2010? You can pause the video here for just 1 minute to see if you can figure that out. The key to remembering to answering that question is to realize that 0 years have passed since 2010 in 2010. So if I changed X into 0 and I evaluated this equation, what would I get for my value? And remember, anything to the power of 0, in other words, if X is equal to 0, 1.1 to the power of 0 is always equal to 1. And 100 times 1 is 100. Of course, the other way to recognize this, and this is connected to today's lesson more, is to realize that in an exponential equation, this number in front that's being multiplied by the power, that is your initial value. And so in this example, 100 was the initial value of one share of Lariat Studios. So in 2010, one share was worth 100. What is the growth rate per year? In other words, by what percentage is it growing? Just from our notes here, the equations, remember that the equations of exponential growth, which is what this is always expressed as y equals a times b, where b, the base, is 1 plus or minus r, and r is the growth rate. So I'm just going to highlight these for us. Remember, the value, that's y. This is in the same structure as this is. 100, that's our initial value. That's how I knew that it started at $100. The base, b, is 1.10. And remember, the base is equal to 1 plus r, because this is a growth equation. In this case, if 1.1, if this is the base, and that's equal to 1 plus the growth rate, how do I find out what just the growth rate is? How do I get r all by itself? I will minus 1, because I'm trying to get rid of plus 1. And that will get rid of it because they are opposites. And then I have to minus 1 from the other side as well, and I get 0.10 equals r. What does this mean? That means that r is 0.10, or if we want to express that as a percentage, we can take this and multiply it by 100 to get 10%. And what does this mean? This means that each of Lariat Studio shares, they grow by 10% every single year. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.